Today I will be talking about learning one count automata using polynomially mini queries. This is a joint work with Dr. Srijit Devi from IIT Goa and Dr. Vasu Penal from University of Bodu. First of all, let's see what a deterministic real-time one count automata or DROCA is. You can think of it as a finite state machine that have access to a counter. So the finite state machine reads from an input type, and on a transition it can increment or decrement the counter. The finite state machine also can do a zero test on the counter. So this essentially means that the finite state machine has two sets of transition function, one for counter value 0 and the other for positive counter value. The counter value of the one counter automata or DROCA always remains positive, and the transitions of this finite state machine are deterministic. You do not have any epsilon transitions in a deterministic real time one counter automata. Now let's look at an example of a DROCA. So this is a DROCA that recognizes language A raised to n, B raised to n, A. So we have three states Q0, Q1, Q2. Q0 is initial state and Q2 is a final state. Okay. So this is your finite state machine, this is your counter and this is your input type. So let's just say, let's just look at this DROCA. You have a transition from Q0 to Q1. So this transition is labeled B plus minus 1, meaning that this transition can be taken on reading a B if your counter value is positive, and this transition will decrement your counter value by 1. Okay, similarly this transition from Q1 to Q2 can be taken on reading an A if the counter value is 0 and it increments the counter value by 1. So the transition here on Q0 to Q0 can be taken on an A if the counter value is 0 or positive and it increments the counter value by 1. So if you look at this DROCA, you can see that on the initial set of A's, it increments the counter and stays in Q0. On seeing the first B, it goes from Q0 to Q1 and decrements the counter. On successive B's, it will stay in Q1 and decrement the counter. So if you have seen equal number of A's and B's, then your counter value will become 0. And then on the last A, it can take this transition from Q1 to Q2 on an A that increments the counter, and that word is accepted. So a word is said to be accepted if you can start from the initial state and then reach a final state on reading that word. Okay. So let's say if you have A, B, B, A in your input type, initially your counter value is 0, you are in state Q0. You increment your counter by 1 on this transition and your counter becomes 1 and you are in state Q0. On the next A, again you increment your counter by 1, you are in Q0. On seeing the first B, you take this transition from Q0 to Q1 and decrement your counter by 1, so your counter becomes 1. On the next B, again your counter value is positive, so you can take this transition. You decrement your counter by 1 and your counter becomes 0. Now on reading the next A, your counter is 0, so you can take this transition from Q1 to Q2 and reach the final state. So the word AABBA is accepted by this DROCA. Note that this DROCA is not complete. For instance, you have not drawn any transition from state Q2, you have not drawn a transition on B from counter value 0. So you can add those transitions by adding an additional state and then make this DROCA complete. Okay, so this is still a DROCA that recognizes language A raised to n, B raised to n, A, and all other words are rejected. Okay, so let's look at the active learning of DROCAs. So what is active learning? In an active learning setup, you have a learner and a teacher. The teacher will have a language or automata in their mind, and the learner tries to learn this language or automata by querying the teacher. So the teacher will give some response to the learner's query, and based on this response, the learner will try to construct a model, okay, that is equivalent to the teacher's. So in the context of DFA, Gold in 78 showed that inferring a smallest DFA from a set of labeled samples is NP complete. This is the passive learning of DFAs. In 87, Angloin gave an active learning algorithm for DFA that runs in polynomial time. It uses membership and equivalence query. Now in the context of one counter automata, Fahmy and Roos in 95 gave an algorithm for learning real-time one counter automata. However, this algorithm needed exponential time and exponential mini queries. Later in 2010, Neural Learning gave a learning algorithm for visibly and one counter automata. So what are visibly one counter automata? These are one counter automata where the counter actions are dependent only on the input symbol. So for instance, you could have something like whenever I see an A, I increment my counter, and whenever I see a B, I decrement the counter. Okay. So let's say I have this restriction. Now the counter actions or the increment or decrement operation on the counter is now dependent only on the input symbol and not on the state in which you are in. Okay. So these kinds of system are called visibly one counter automata. So this algorithm for learning visibly one count automata also required exponential time and exponentially many queries. Now in 2022, Brewer et al. Extended this idea for learning DROCA with an additional counter value query. So here the learner will give a teacher a word and ask what is the counter value reached on reading that word. So in this setting, they showed that DROCA can be learned using exponential mini queries and in exponential time. Okay, so so what are the difficulties in learning DROCAs? There are three main issues. One is the running time of the equivalence query. The equivalence of two DROCAs of size less than or equal to n can be checked in polynomial time, but the polynomial is huge. For instance, for two n state DROCAs, the equivalence check will take at least some order of n raised to 26 times. So this is not practical. This cannot be used for practical applications. The second is the number of queries. The number of queries for all the existing learning algorithms are exponential. And the third is the total time taken to learn. So this is also an exponential. So in this talk, we address the first two bottleneck. So first we propose a faster equivalence or a practical equivalence query. As we discussed, all the existing algorithms need some order of n raised to 26 time for checking equivalence. So we propose counter synchronous equivalence. Now what is counter synchronous equivalence? You have two DROCAs. You say that they are counter synchronous if they reach the same counter value on all words. For instance, you can consider the following two DROCAs. These both of them recognize the language A raised to n, B raised to n, A. Okay. So here the counter value reached on the first mission is same as the counter value reached on the second mission for all words. Okay, they are also language equivalent. However, they are not isomorphic. For instance, you can see here you have a transition from Q0 to Q1 on an A equal to 0 that increments the counter by 1. Whereas in the second mission, this A equal to 0 transition is a self loop on Q0. Okay. So these are counter synchronous and equivalent. One can also construct TACAS that are counter synchronous but not equivalent. For instance, consider the first DROCA. You interchange the final state and non-final state. You make Q0, Q1, Q3 final and Q2 non-final. This automata would be counter synchronous with this but not equivalent. So what is our theorem? We have that for two DROCs of size n that are either not counter synchronous or not equivalent, there is an order of n raised to 6 time algorithm to find a word W such that either W is accepted by exactly one of the DROCs or the counter value of W is different on both DROCs. So you can find a word that is accepted by only one of these machines or a word W such that the counter value reached on that word is different on both the machines. Okay. So this algorithm takes only order of n raised to 6 time and hence can be used in practice. So for visibly one count automata, we have an even faster algorithm that runs in order of n cube time for checking their equivalence. Now this is the proposed method, we call it min-OCA. So in this learning setup, you have three kinds of queries. One is a membership query where the learner gives the teacher a word W and asks whether the word is in the language of the automata the teacher has in mind. So let's say the automata the teacher has in mind is A. We'll ask whether that word is accepted by the automaton A. The teacher will respond yes if the word is in that language or no otherwise. So second kind of query is a counter value query where the learner gives the teacher a word W and asks what is the counter value reached on reading that W, and the teacher will return the corresponding counter value. The third query is a minimal equivalence query where the learner presents the teacher a model B and asks whether B is equivalent to the DROCA A the teacher has in mind. The teacher responds yes if both the DROCs are equivalent or no and the smallest counter example. So the counter example either is a word that is accepted by one machine and not by the other, or is a word for which both the machines reach different counter values. So the proposed method min-OCA is an active learning algorithm for DROCA. We show that min-OCA requires only polynomial mini queries to the teacher and uses a SAT solver. It also returns a minimal counter synchronous DROCA with respect to the teacher's DROCA, and our evaluation showed that it outperforms the existing technique. So what is the main idea behind min-OCA? It is to learn a characteristic DFA. So we will define what a characteristic DFA is. So this is the DROCA that we saw before that recognizes the language A raised to n, B raised to n, A. Okay. and this is the corresponding characteristic DFA. So let's say your DROCA is over the input alphabet AB, then your characteristic DFA will be over the input alphabet A0, A1, B0, B1. So you have 4 states U0, Q1, Q2, Q3, and in the characteristic DFA you will have the same set of states, and the transitions also kind of look the same, but the labeling is different. Okay. So here you had a transition from Q0 to Q1 on a B when your counter value is positive. So in the characteristic DFA you will have a transition from Q0 to Q1 on a B1. Okay. So from Q1 to Q2 you had a transition on A for 0 counter value. So in the characteristic DFA you will have a transition from Q1 to Q2 on an A0. Similarly, here you had a transition on B plus, so we will have a transition on B1. From Q0 to Q0, you have a transition on A0 and A plus. So in the characteristic DFA, you will have a transition on A0 and A1. Okay, so you do that for all the transitions, and what you get is a characteristic DFA. So you can see that given a DROCA, one can easily construct this characteristic DFA. Okay. However, given a characteristic DFA, getting a DROCA is slightly more difficult because you don't have this counteraction. So here this transition only tells you that this transition was taken on a B when your counter value is positive, but it will not give you any information regarding what happened to the counter on taking this transition. So if you have some magical way of knowing this counteraction, then you can put this counteraction back and then get a DROCA. So the main idea behind MinOCA is to trick the system into kind of learning this characteristic DFA first, and then use the counter value information to find this counteractions on a transition and get the DROCA back. So now, before going ahead, we will kind of look at the observation table that we have. So we will keep track of the following information. So let's say this is an example of an observation table that we keep during the learning. So here you have a prefix closed set of strings. Let's call them rows, and you have a suffix closed set of strings. Let's call them columns. So in the rows you have epsilon, A, AB, and ABA, and you have the one letter extensions in the bottom part. Okay, so you have BAA, ABB, ABAA, and ABAB. So each row will have an associated counter value, which is the counter value reached on reading that word. So this is the counter value reached on reading epsilon, counter value reached on reading A, counter value reached on reading AB, counter value on reading ABA, and so on. Okay. Now you look at the column epsilon, epsilon here. Okay. So this will denote the membership of the word epsilon dot epsilon. So this word is rejected, A dot epsilon is rejected, AB dot epsilon is rejected. However, ABA dot epsilon is a word that is accepted, so you will have 1 in the corresponding cell. Okay. So this is counter value, this is membership. Now what about this column actions? So this is a triple where the first entry denotes what is the current sign of the counter value. So for this particular entry, it will denote what is the sign of the counter value that you have on reading this word, after reading this word A. So after reading A, your counter value is 1. So the sign would be 1. Okay. So the sign is 1 if your counter value is positive, the sign will be 0 if your counter value is 0. Okay. Now what are the next two entries? So the next entry will denote the counteraction of on an A after reading an A from this position. Okay. So here you have read an A, your counter value is 1. If you read another A after reading this A, then your counter becomes 2. So this would be a plus 1. Now this would be the counteraction on reading a B after reading an A. So counter value of A is 1. On reading a B, you decrement your counter by 1. So your counteraction will be minus 1. So this is kind of a look ahead on what happens to the counter after reading this word. Okay, so you do that for all the words, and this is what you have. Now in this table, I have colored 2 rows with the same color if they are equal. Okay, so here these are colored yellow, means the entries are the same. Now we have 2 definitions, one is closed and other is consistent. So the first is declosed. So when do we say that a table is not declosed? So this table here is not one closed. Why? Because you have a row with counter value 1 in the bottom part of the table, which is not present in the top part. Okay, so this is not one closed. So how do we make a table closed? Okay, so this is not one closed, so we add this B to the top part of the table and add its one letter extensions to the bottom part to make it closed. So now you can see you have 2 rows with counter value 1 in the bottom part which are already present in the top part. So this table is now one closed. However, you can see it is not two closed because these rows are not in the top part. So this is the definition of a D-closed table. Now what is D consistent? You have two rows with counter value less than or equal to D in the top part having the same color, but their one letter extensions are having different color. So for instance, this table is not zero consistent because epsilon and AB have the same color, they have the same counter value. However, epsilon dot A is this purple, has purple color, while AB dot A has this orange color. So these epsilon and AB have the same color, but their one letter extensions have different color. In that case, we add this A to the table and X in the table, okay, so that epsilon and AB becomes different color. So this table is now one consistent. Now, so we also do a conversion in a learning algorithm for every word in your observation table. So your words are over the alphabet AB. You convert that word into the modified alphabet A0, A1, B0, B1. So let's just say if you have ABA, this word will be converted to A0, B1, A0, Y. Okay. So this is basically you are encoding the counter information in the word. So initially on reading, before reading the first A, your counter value is 0. So your first A will become an A0. After reading the first A, your counter value has become 1. So the next B will become a B1. After reading AB, your counter value is 0. So the last A will become A0. So the last A will become an A0. So you do that for all the words in your table in the during your learning algorithm. So we will see how the learning algorithm proceeds. So initially you have an observation table with just rows equal to epsilon and columns equal to epsilon and your D equal to 0. You will construct a D-closed, D-consistent observation table using membership and counter value query. So this table is D-closed and D-consistent. Once you have a D-closed and D-consistent observation table, what we will do, we will convert this entries of this table into the modified alphabet. So here epsilon is a word that is not accepted. So you have two sets, pos and neg. So pos will have the set of all accepting words and neg will have the set of all rejecting words. So here all words are rejecting. So you will convert every word into its modified alphabet. Epsilon will be neg, A will become A0, B will become B0. Okay. However, you do not have any accepting words in this table, so your pos will be empty. So the idea is now to find a separating DFA for the pos and neg. However, this information is not sufficient for us to get a characteristic DFA. You will also have to encode the counter actions in the pos and neg. So let's just say I call this first entry X, the counteraction of A, Y and the counteraction of B, this tuple Z. Okay. I will also encode this information and add words to pos and neg. So X is the counteraction corresponding to epsilon. So I will add epsilon X to my pos. Also I will add A0Y to my pos and B0Z to my pos. However, B and A and B have different counteractions. So I will add A0Z to my neg and B0Y to my neg. Okay. So my pos and neg will be the following. So the idea is now to find a minimal separating DFA. A minimal separating DFA is a DFA that accepts all strings in pos and rejects all strings in neg and has the minimal number of states. So the minimal separating DFA, like we discussed before, finding a minimal separating DFA is an NP complete problem. So we use a SAT solver to find this separating DFA. So in this case, this will be a minimal separating DFA. It accepts all words in your pos. So X is accepted, A0Y is accepted, B0Z is accepted, and all other words are rejected. Everything in neg is also rejected. Okay. So you find a minimal separating DFA for your pos and neg. Once you have done that, you remove the transitions on these counter actions X, Y and Z. So here you will remove this transition on this X, Y and Z and this is what you get. So this state is an unreachable state, you remove that and what you get is a characteristic DFA. Now what will you do? You will look at your observation table and from this characteristic DFA you will put the counter actions back to get a DROCA. Once you have this DROCA, you give this DROCA to the teacher and ask a minimal equivalence query. The teacher will either respond yes. If the teacher responds yes, you are done, you have learned the right DROC, or the teacher will return a minimal counter example. So in this case, the teacher returns a counter example ABA. You will add the counter example ABA and all its prefixes to the observation table. You increment your value of D and then repeat the process until you get the right DROC. So if the teacher returns yes, you stop and output the learned DROC. So we have implemented this learning algorithm in Python and we have compared with the existing technique by Brewer, Perret and Stuckey, which we call BPS, and these are the results that we got. So we generated DROCs, random DROCs of number of states ranging from 2 to 15 and input alphabet size ranging from 2 to 5. We generated 100 random DROCs for each input alphabet size and number of state pair, and we ran both the algorithms for 5 minutes on each of the generated samples, and we recorded the number of samples that both the algorithms were able to learn. So the red line denotes the number of DROCs that the proposed method MinOCA could learn, and the blue dotted line here denotes the number of languages the existing algorithm BPS could learn. So you can see that MinOCA kind of outperforms the existing technique in the number of languages learned. So in under 5 minutes, it can learn all languages DROCs of size up to 11, whereas existing one can learn up to 4 or 5. Now we also, so the second graph here shows the length of the counterexample returned by the teacher on an equivalence query. So MinOCA always returns the minimal counterexample, so we have a line like this, whereas the existing one uses an approximate equivalence set. So like we discussed before, the exact equivalence cannot be used in practice because of its high complexity. So they are using an approximate equivalence set and they are getting larger counterexamples. So the third graph here shows the average number of states in the learned DROC. MinOCA always learns a minimal counter-synchronous DROC, and hence the number of states in the learned DROC is less than or equal to the number of states of the teacher's DROC, whereas the existing one does not have any guarantee and can learn arbitrarily large DROCs. The fourth graph here shows the average number of equivalence queries used. MinOCA theoretically uses only polynomially many equivalence queries, whereas BPS requires exponentially many, and that is reflected in the graph. So these are some examples of DROCs learned by MinOCA and BPS. So let's say this was the input DROCA that recognizes the language A raised to B raised to A. This is the DROCA learned by MinOCA, which is counter-synchronous and equivalent. However, BPS learns a larger DROCA that is equivalent but not counter-synchronous. So is it always the case that MinOCA always learns a minimal DROCA? Not necessarily. Something like this could happen. So this is the input DROCA. The language is essentially a regular language. So it accepts all words that does not contain a B. However, it does some random counteractions in the process. So MinOCA will also try to mimic this counteraction and will learn a minimal counter-synchronous with respect to the teacher and will end up learning this DROCA. Whereas BPS might just learn the language, recognize that it is regular and then just learn this language. Okay. So this is smaller with respect to the input, but this is still the minimal counter-synchronous with respect to the input. So in summary, we have an active learning algorithm for DROCA. It uses 3 types of queries: membership, counter value and minimal equivalence query. We saw that the existing algorithms for active learning of TACAS need exponentially many queries. So the proposed algorithm uses a SAT solver and requires only polynomial many queries, and it learns a minimal counter synchronous DROCA. So our experiments show that MinOCA can learn DROCs up to size 10 in under 5 minutes, which is better than the existing technique. Now future work. So the major bottleneck for learning DROCA is the equivalence set. So we know that it is polynomial, but the polynomials are huge. So can we have a better equivalence check for DROCs? So this is one question that one can try to answer. And the bottleneck for using MinOCA is actually the difficulty in finding the minimal separated DFA. So we can have a faster algorithm for learning DROCs if there is a faster and better way to find the minimal separated DFA. The final question is, does there exist a polynomial time algorithm for learning DROCs theoretically? And we have recently answered this question. There is indeed a polynomial time algorithm for learning DROCs, and the result will be published in LIX 2025. So the paper is called Learning Deterministic One-Count Automata in Polynomial Time. So these are the references, the learning algorithms. Thank you.